So this is how you estimate the focal length of the convex lens. So what you have to do, you have to place the screen and the convex lens and let the light come from infinity, and you have to move the screen or the lens until you get a very sharp image on the screen, and then you note down the distance between the screen and this convex lens, which is about 18.5 centimeter here. So that is the rough focal length. So let's begin the experiment. The experiment aim is to find the focal length of convex lens by graphical method, not by using the formula but by graphical method. So the principle of the experiment is the object distance must be greater than the focal length of the convex lens to get a real and inverted image, and when the object distance is twice the focal length, the image distance will also be twice the focal length. So what does that mean? So this is the convex lens, this is the focal length, and this is the twice the focal length. So if we place the object such that the object distance, that is from the convex lens to the object, so if this distance is greater than f, only then you will get a real image, a real and inverted image, which will be magnified also. And if you place the object at exactly at 2f, then the image will also be at 2f and the size won't be magnified. So it will be real but not magnified or diminished, it will be of the same size. Now the problem here is, if we keep the object very close to f, then the image formed will be very magnified. Maybe here it will be very magnified, and the intensity will be very less. So it is usually better if we keep the object away from f, maybe at 1.5 times f or something like that, but away from f. But the problem is we don't know f. That is the aim of the experiment. So what we can do, we can either calculate rough focal length, which I will add how to calculate rough focal length, or you can go by trial and error method. So what do I mean? You have to place the object somewhere. So you don't know f, so you place the object somewhere. If the image is very magnified, then you change that position. I'll show you what I mean. So this is the apparatus, that's the object is the grid, not the bulb. This is the convex lens, and that's the screen. Now I will place the convex lens very near to the object. Maybe here I am very near to focal length, so I should not place the convex lens here, because now the image will be very magnified. As you can see, the image I am getting here, I am still not getting the image. Okay, somewhere here I am getting the image when the convex lens is here. The image is very magnified and very feeble. I can barely see. So you have to avoid these positions. So what you can do, for the just increase the object distance and see where you are getting the image. Okay, now you can see that the image is not so magnified and more intense also. So this is a better position. So that's how you can judge where the object position must be. Either that, or you can calculate the rough focal length, that is around 18 centimeter. Then you know that you have to place the object further away from 18 centimeter. Maybe you can place at 28 centimeter or something. All right. So that's what the note says. If the object is beyond focal length but near it, that means around here somewhere, then the image will be much further beyond 2f, so maybe here or somewhere, and it will be very magnified. So therefore, as a general practical rule, it is better to keep the object in the range 1.5 times rough focal length to 2 times rough focal length. So we have already calculated rough focal length, so we have to place the object for the first observation at around 1.5 times rough focal length. So if rough focal length is 18, maybe around 28 centimeter, you can keep the object and then start taking observations. So if you don't have if you can't calculate rough focal length, then I told you to calculate by trial and error method. Now this is the formula and the nature of graph. So let me see, I have drawn the bigger one here. So as I told you earlier, now you have to calculate the focal length of the convex lens using the graphical method, which is, the graph is u minus u versus v graph. So what is u? U is the image distance, u is the object distance, and v is the image distance. V will be on the y-axis, minus u will be on the negative x-axis. So after you plot u and v, you will get a curve like this, and then you have to draw a line exactly at 45 degree with the either of the axis, and wherever that line cuts the curve, you have to drop two perpendiculars. Now this is supposed to form a square of side 2f. Now you can measure the value of 2f here. So for example, from OA, this side you can measure on the x-axis from here to here. Maybe OA you will get some value, similarly OB you will get some other value on the y-axis, then you will take the average of both of them to get the focal length. Now this carries again 2 marks, nature of graph and as well as the formula. Then the observation table looks something like this. I have already taken the values. I'll show you 2 of the values. So you have to take at least 6 observations because you are plotting the graph. Now I'll show you how to take the observations. So now let's start with the observations. So as you can see, rough focal length I had already calculated. It came out to be around 18.5 centimeter. So let me take 18 centimeter since it is anyway rough value. So now my object distance for first observation, which should be around 1.5 times 18, which is 27 centimeter. So I don't like odd values, so let me take 28 centimeter. Now if you could not calculate rough focal length, so then you can just keep it at some value where the magnification is not very high, as I showed you in the trial error basis method. So now we can see here I have placed the convex lens at 28 centimeter, and you can see that the image is not very magnified and it's quite intense also. So basically you have to move the screen until you get a very sharp image. I got an image at 77.7 centimeter. So the object distance is 28 centimeter because 28 minus 0, I placed the object at 0. So 28 minus 0 is the object distance, which is 28 centimeter. From sign convention it is minus 28, and then the image distance is 77.6 or 77.5 minus 28, and that's positive, that's the image distance. So I have written here at 28 centimeter minus 28 centimeter, the image distance is 77.5 minus 28, which is 49.5 centimeter. Then for the next observation, keep on increasing by 2 centimeter and calculate the image distance. You can notice a trend here that the image distance keeps on decreasing, and at some point it becomes almost equal to the object distance. You can see here object distance is 36 and image distance is almost 36. So this, as I have told you earlier, happens at 2f position. So you can see the image here. I have told you this is the principle. When the object distance is twice the focal length, the image distance is also twice the focal length. So that's what happening here. When the object distance is twice the focal length, the image distance is also almost twice the focal length. So here only you can calculate f to be 36 by 2, which is 18. That is also our focal length. Okay, so now actually what you have to do, you have to plot the graph here. I have already plotted the graph. So this is the graph. So in the y-axis you have to plot v, that is the image distance, and x-axis minus u. So write the scale also. And one thing you have to notice here is that the scale should be uniform for both the axes. So for example here for x-axis, that is minus u, I have taken the scale as 1 centimeter equal to 1 centimeter. So that means I have started from 28, and this is 29, and this is 30, 31, 32, so on. And in the v-axis also it should start from 28, and also the scale should be similar to same as x-axis. So here also it's 28, and this is 29, 30, and so on. So basically it should be a square. So if it starts from 28 and ends at 40, this also should start from 28, and it can end anywhere, but the scale should be uniform. So you can see 28, 29, 30, here also 28, 29, 30. Now I have plotted these values, and I'll get a curve like this, and then at 45 degree, so this is about 45 degree, I have drawn a line, and where it intercepts here I have dropped 2 perpendiculars, and I have measured the length of this 2 perpendiculars from here to here. That is 35.6 because it is around 35.6. As you can see, this is 34, this is 35, and this is 35.6, and similarly this length is around 35.8. so you can see here around this is 35, so it's around 35.8. I'll take the average of both of this using this formula. So I got the f average to be around 17.85 centimeter, which is close to our focal length. So the result of our experiment is that the focal length is 17.85 centimeter. Let me just show you one more observation here. Let me keep it at 30 centimeter. Okay, this is at 30. Now you can see that the image is quite blurred, so I have to move the screen. Okay, now the image is clear. Now you have to note down the image distance. You have to note down where the image is forming on the screen, so that's why you have to note down the scale corresponding to the screen, so which is around 75.5 or 75.6. So the image distance is 75.5 minus 30 centimeter and the object distance is minus 30. So like that you have to plot the graph and get the result. Now let me keep the convex lens at exactly at 36 centimeter, and let me confirm that the image is forming at around 36 centimeter, and it that means at 2f position, which means the image size should be of the same size as the object. That means there should not be any magnification. So basically I'm placing the object at 2f, so the image is also forming at 2f. We already saw that if we place the object between 2f and f, the image will be magnified and it will be beyond 2f. So now I have placed the object here at 2f, so the image will also be at 2f and it won't be magnified. So from the observations we know that it's around 36 centimeter, that's the position of 2f. So I have kept the convex lens at 36 centimeter and the image is forming at around 71.5, so the image distance is 35.5. So this is the image. As you can see, that is almost the same size as the object. Now that means if I move the convex lens beyond 2f, that is in this direction, so the image should diminish, and if I move the convex lens in this direction, so that means below 2f, the image should magnify. So now I will move the convex lens beyond 2f and just observe the image, it should diminish. You can see it is getting diminished. So now I will move the object beyond near the object, so that means it should get magnified. So it is getting magnified. So that means 36 centimeter is the position of 2f. So your experiment is verified.